electricity unit, like the class questions and quizzes,
Mm-hmm.
the electric potential is what's kind of like tripping me up, but slowly getting it back.
Mm-hmm. How's it going, Bodhi? Welcome, everyone. Welcome.
I've never been to one of these side pass sessions.
Yeah, a side pass. It's generally pretty chill. We just sort of sit here and we talk about things and we go over practice problems and stuff. Here, I'm gonna go ahead and drop an attendance link in the session text chat. If you guys can fill that out, it'd be greatly appreciated. So let's talk about electric fields. It's been a few months since you guys have had to take a look at those. You guys have been more focused on magnetic fields since then. But so, first off, how would we find the electric field due to a single point charge in space? Let's say we just have a single point charge right here. What's our electric field going to look like due to this point charge? And how do we find it? Welcome, Mohammed. What is our electric field due to a single point charge going to look like? Let's assume it's positive.
It would be pointing away from it,
Mm-hmm.
all around the point charge.
Yep, it's going to point away from it. And what's it going to do as we move outward from the charge?
Its strength is going to get weaker.
Yep, exactly. So essentially, as we move outward, the strength of the electric field is going to get weaker. As a function of what? Like if the distance away from it is r, how does the electric field decrease? Or first of all, how do we what is the electric field itself? Like what is it mathematically? What law do we use to find the electric field due to a point charge? It starts with the C.
Cool.
Exactly, Coulomb's law. What is Coulomb's law?
AQ1, Q2 over R squared.
Yep. So is our electric field is going to be K Q1 is times Q2, or this is the force, right? This is the force between two acting on two charges.
Yeah.
So how do we actually get the electric field due to one charge? So here, I'll write down what you just said. So the force acting between two charges is K Q1 Q2 over R squared in the r hat direction. How do we actually get the electric field? How does it differ from our force here? You're breaking up a little bit. I couldn't quite hear you.
You divide the force by one of the point charges.
So you're saying we get rid of one of the two charges?
Yeah. Well, you only keep the charge that you're trying to measure the electric field of.
Exactly. So if this is Q1, our electric field generated by that charge is going to be K times Q over R squared. And in what direction?
R hat direction.
Yep, exactly. It's useful to remember the r hat direction because if you then start adding vectors, you need to remember what the r hat direction is for each. So that's how you get the electric field. So therefore, from this, how would we relate the force on a charge and the electric field it's in? Like if we have an electric field going to the right and we have a charge here, this is Q2. How do you relate the force on it to the electric field? If we look up here, if this is Q1 that's generating the electric field. Go ahead, Mohammed.
Force is equal to the charge multiplied by the electric field.
Yep, exactly. It's that simple. So our force acting on our charge is going to be the charge itself times the electric field that it's in. And so if that electric field that it's in is being generated by another charge, it's kq1 over r squared. And so then we get the force acting on it would be our force due to two charges, as we'd expect. So now, that's how we get the electric field from one singular charge. What happens if we have multiple charges? Let's say we have, different example over here. We're going to have like 3 charges here. Let's just assume they're all positive. How would we get the electric field, let's say, right here? How would we get our electric field due to 3 separate point charges?
You'd have to basically like see like what's the electric field between like the point where you're trying to find it at and the 3 charges separately.
Exactly, each charge individually. Keep going.
So then like it would be like based off of like what each individual charge is, and the radius is obviously going to be different for each charge because they're at a different distance away from the point.
Mm-hmm. And so then once you have each individual one, let's say, for example, we have, draw it in red, we have the first electric field here from this charge, second electric field here from this charge, and a third one here from this charge. What do we do once we have all those individual electric fields?
We just sum it together, right?
Exactly. So do we just add together the magnitudes of all 3?
Would it just be the magnitude? I thought we'd have taken into consideration the sign.
Not just the sign. We're acting in space here, right? We also have to worry about the direction, right?
Yeah.
What's a quantity that has both direction and magnitude?
A vector?
Exactly. Cue that scene from Despicable Me. So essentially we have to vectorially add all 3 of these together. How do we add vectors? What are 2 ways we can add vectors?
Don't you like put the bottoms of the vector on the top of the vector or something? And
Yeah.
then, yeah.
Exactly. So like we can visually add them by like, let's say let's do this one first. We're going to take the second vector and sort of add it to the end. Take the third vector, add it to the end of that, and boom, that would be our total net vector. It looks something like that. Now, what about if we are actually given numbers? How would we actually go ahead? What's the easiest way to add vectors together in, let's say, 2D space?
Pythagorean theorem.
And so take me through the process.
It'd be like, square root of like one of the vectors squared plus the other vector squared, and then you can, since we have 3 here, you can just use what you get for the first one, and then do the Pythagorean theorem again for the second.
And so how do you take into consideration the direction? Because you're just talking about magnitudes and whatnot here.
Yeah.
How do we take into consideration direction? Does he give you any hints in your formula sheet? No, he doesn't. It's pretty simple, like geometry and trigonometry. Well, let's use the Pythagorean theorem, right? We have a vector let's say it looks something like this. And we have, let's say, the angle it makes with respect to the x-axis. And we have its magnitude. Let's call it m. What can we do with this vector?
For one, we can look for like the x component and y component.
Exactly. X component and y component. So we can break it down into an x component and a y component. How do we do that, by the way?
So the x component it's basically we form like a triangle,
Mm-hmm.
right? And we use it based on like the sine cosine.
Yep.
For the angle available.
So in this case, is the x component cosine or sine?
Cosine.
Cosine. Exactly. SOHCAHTOA. Sine is opposite over hypotenuse, so sine would be the y component, and cosine is adjacent over hypotenuse. It'd be the x component. So once we break each of our vectors into x and y components, what do we do? Do we just add all the x components together and add all the y components together? Is it as simple as that?
No.
I go with a yes.
Ooh, we have conflicting answers here.
Uh-oh.
Is one of you overthinking, or is the other one of you underthinking?
Wait, so what's the goal for this?
We want to find the total net vector. Essentially, we're trying to find the net electric field.
Net electric field.
So we break each of them into x.
Well, because we just add all the vectors together, so...
Exactly. So to add all the vectors together, Harsha was overthinking. Yeah, we literally just add the x components together, add the y components together. And then you get a total net x component and net y component. And usually we don't really care about breaking it back into a single magnitude. But if you wanted to, how would you do it?
Pythagorean theorem.
Exactly. Pythagorean theorem. X squared plus y squared is equal to, I guess, magnitude squared, z squared, whatever. You know what I mean. H squared. We'll call it h, hypotenuse. So that's how you get magnitude of multiple, that's how you get the net electric field for multiple charges. So now one more thing. What's Gauss's law? Didn't remember back from 2 months ago. What's Gauss's law?
Integral E dot dA equals Q enclosed over epsilon naught.
So we have the integral of,
The closed surface.
yep, closed integral of E dot dA is equal to Q enclosed over epsilon naught. Wonderful. What the hell does that mean? What are each of these things? What is E? Well, we can assume E is the electric field. But what's everything else? What's going on?
dA is like the area vector.
Mm-hmm. For a surface. And then Q enclosed is...
The charge that's enclosed within the Gaussian surface.
Exactly. And then epsilon naught is just a constant. So what is a Gaussian surface?
Like an imaginary thing that's like around what we're trying to find the electric field or electric flux around.
Mm-hmm. Exactly. And what sort of imaginary surfaces, what sort of situations can we use these imaginary surfaces in?
When it's like symmetrical.
Symmetry. Exactly. What are our 3 types of symmetry?
Spherical,
Mm-hmm.
cylindrical, and planar.
Exactly. So first of all, spherical. What does our Gaussian surface look like for a sphere of charge or a spherically symmetric situation? would just be another sphere surrounding it, right? It's just going to look something like this. What about if we have a cylinder? So we're going to have something, bear with me with the 2D drawing of a 3D object. What is our Gaussian surface for a cylinder going to look like?
Can be a cylinder.
Yep, exactly. It's going to be another bigger cylinder that's going to go ahead and surround it. Now, what about, you said, what was the last one you mentioned?
Planar.
Planar, exactly. So let's say we have a, let me actually draw this manually. So we'll imagine we have like an infinite plane of charge. What is our Gaussian surface for a plane going to look like? We can't just have another plane, because then our Gaussian surface would be infinite, right?
Yeah.
So how do we, what is our Gaussian surface going to look like for a plane?
Wouldn't it be like a rectangular prism?
Mm-hmm. You can use a rectangular prism. Or literally any sort of prism you want. We can use a triangular prism. I think Dr. G likes to use cylindrical prisms. So basically, the cylinder looks similar to our cylindrical surface, Gaussian surfaces. But so it's going to be some sort of a prism. How do we orient it? Welcome, Dereje and Faniel, just hopping in. If anyone hasn't already, if you could fill out the attendance form in session text, that would be greatly appreciated. Thank you. So how do we orient our prism for our infinite surface? Is it going to go through our surface?
Yeah.
And so it's going to look something like this, right? Let's say I'll draw a cylindrical prism, because I'm pretty sure that's what Dr. G likes to do. So it's going to go here, it's going to go through our surface, and it's going to come out the other side. So those are our three symmetrical cases where we are able to use Gauss's law. Gauss's law is this E dot dA is equal to Q enclosed over epsilon dot. So we know what Gauss's law is. We know what our Gaussian surfaces are, where dA is like the area vector coming out. So what do we actually use Gauss's law for?
Find the electric flux.
Find the electric flux, which then do we really care about electric flux at the end of the day?
I don't.
Yeah, I don't either. Dr. G doesn't either. But what can we use electric flux to find? What do we care about?
The electric field.
Exactly. We want to find the electric field itself. Because Gauss's law is just the definition of flux. Does he actually give it to here? Yeah. So the electric flux itself is this integral. But we don't really care about electric flux, but we want to find the electric field. How do we find the electric field using Gauss's law? For our Gaussian surfaces, we said there was some sort of symmetry, right?
I don't know what so on formula sheet there's like this symbol divided by 2. E up, E naught.
Are you taking a look at your formula sheet?
Yeah. So right under the flux equation.
Mm-hmm.
That's how we can find the electric field.
That's what you actually get when you use Gauss's law.
That's not what we use Gauss's law.
So once we've already used Gauss's law, we can derive this for an infinite plane.
Okay.
But how do we actually go through that process? Well, first of all, I like to start with this dot product. What's going on here with the dot product? What is a dot product? How can we simplify the dot product? Give you a hint. It's in the formula sheet.
So the two vectors, or the two vectors would equal to their magnitude multiplied by cos theta.
Exactly. So we have, it's actually right here. So the dot product of two vectors is equal to the magnitudes of the vectors times the cosine of the angle between them. So we have the integral of E dA, and then we have cosine of theta. How does that cosine of theta go away? Why can't it go away?
Maximum value, I think.
So what is the angle?
For it to be 0.
It would have to be 0, right? So is that why we have to have our symmetric charge distributions? Is that why we have our symmetric Gaussian surfaces? I mean, let's take a look. We know the electric field for a sphere of charge is always going to be outward, right? And our dA area vector is also outward. So that checks out. Same thing for our cylindrical Gaussian surface. We have, let's worry about the end caps in a second, but for the perimeter of our cylinder, I don't know words, but you guys know what I mean, like the part that goes around here. The electric field we know is going to be outward, and the area vector is outward, so that checks out. What about the two end caps of our cylinder? What's the angle between the electric field and the end caps? Area vector. It's going to be out like that.
90 degrees.
90 degrees. What's the cosine of 90?
0.
0. So we can basically ignore the end caps of our Gaussian surface, and it doesn't affect anything in our calculation. Now, what about our planar symmetry situation? For the end caps, the area vector is outward. What direction is the electric field?
In the same direction.
Same direction. So it's 0 degrees, cosine of 0 is 1. And then what about our perimeter? It's 90 degrees again, right?
Mm-hmm.
So we can just ignore the perimeter of our Gaussian surface and just worry about the end caps. Does that make sense? All right, let's go ahead and hop into some examples. So we've talked through Gauss's law, which we'll use in our second example. And then we've also talked through sort of vector adding and finding the electric field due to point charges. So now let's go ahead and take a look at a line of charge. So it's actually a finite line of charge. So it's going to look something like this. It's going to go from, this is 0, goes out to -2 and to +2 centimeters. We have a finite line of charge, the charge density plus 300 microcoulombs per meter. Numbers really don't matter, they're just arbitrary. So first of all, let's take 5 minutes. What would the electric field look like very close to this line? And then also, what would the electric field look like very far from the line? Take 5 minutes, then we'll talk about it. once again, if anyone hasn't filled out the attendance form in the session text, if you could do that, that'd be greatly appreciated. Thank you. All right, so we have our finite line of charge. What is our electric field going to look like when we're very close to the line of charge? So let's say right about here, for example. What would our electric field look like? Or maybe I should ask, what is our line of charge going to look like when we are very close to it?
The electric field would like be, its magnitude would be like pretty big, right?
Mm-hmm.
Since the radius is very small.
Mm-hmm. And if we were to move, slightly further away, let's say just from here to here, for example, how is our electric field going to change? What is it going to look like?
It's going to decrease.
Decrease as a function of what?
Function of the radius.
Mm-hmm. And it's going to be like 1 over r, 1 over r squared, 1 over r cubed.
1 over r.
Why is that?
Because the equation for an infinite line of charge, or not an infinite, for the line of charge would be 2k lambda over r.
Is that the equation for a finite or an infinite line of charge?
Oh wait, that's infinite line of charge.
That's an infinite line of charge. But we can use that. Why? Why are we able to use that?
Because when you do the integral, or using Gauss's law, you get the same thing.
Well, that would be the case for if we had an infinite line of charge. Like that 2k lambda over r is what you derive, is what you actually get if you use Gauss's law on an infinite line of charge. So, but this isn't an infinite line. Why are we able to treat it as an infinite line? If we're very close to it, the line is effectively going to be infinite compared to how far away from it we are. Right?
Yeah.
So, when we're very close to it, we can essentially approximate the line to be infinite. And so, the electric field is going to be 2k lambda over r in the r hat direction, obviously. So now, what about if we're very far away from the line? What is the line of charge going to look like if we're very far away from it?
Look very small.
Very small. It's
Okay.
almost going to look like what?
Like no wires there.
It's going to be like there's no line, and instead it's all going to be as if it's in one spot, right?
Mm-hmm.
Almost like a point charge. So, what would our electric field very far away look like?
The same as the point charge.
Point charge. And what would the charge of our point charge be?
Kq over r squared.
And what would Q be?
It would just be whatever the Well, you would have to multiply. Oh wait, no, you wouldn't have to. It would just be 300 microcoulombs.
That's our charge density, 300 microcoulombs per meter. That's lambda. How do we get the total charge Q?
Multiplying it by the environmental wire, or the line.
Exactly, the length of the line. So it's going to be K, we have our lambda times the length L. I don't feel like messing with the numbers, and honestly, you guys shouldn't worry about the numbers until you actually go in to enter an answer on your quizzes or on Flip It. So it's going to be K times lambda times L is our total charge over R squared, R hat. That's what our electric field is going to look like if we're very far away from the wire. So when we're very close, the finite line of charge is effectively going to be infinite, and it looks like 2k lambda over r. And when we're very far away from it, our line of charge looks like a point charge, and so our electric field is k times q over r squared, where q is the total charge on the wire, lambda times L. Does anyone have any questions about this? All right, so now how would we actually set up the integral to find the electric field anywhere? Let's take about 5-6 minutes, then we'll go over this. Also, welcome, Kevin. How's it going? So take about 5 minutes, and we'll go over part C here. All right, so how do we actually go ahead and set up an integral in order to find the electric field for this infinite line of charge anywhere? Like, let's choose an arbitrary point here and say xy. How do we actually go ahead and set up an integral to solve for our electric field?
You just use like Fox's law.
Sorry, could you repeat that?
So you set up charge enclosed over epsilon naught equal to the integral of the electric field times the area.
Are we able to do that here? Is our Is our charge distribution symmetrical in all directions?
No, because it's the line. Oh, I guess not. I guess you couldn't do that.
Well, I mean, it's a line, but it's a finite line. If it were an infinite line, we could do that.
Right, yeah.
But it's a finite length. So how would we set up an integral to solve? Well, remember how we talked about earlier when we had, for multiple point charges, we had our 3 electric fields due to our 3 point charges. And the way we find the net electric field is we add them together. We add the vectors one on top of one another. Right? Now, a line of charge is effectively just a bunch of little point charges, right? Going along here. effectively an infinite number of point charges all lined up next to one another. And each one is going to contribute to the electric field. So, how would we actually set that up? Well, let's say, first of all, let's start at this end. So we have our electric field due to this point at the end here. Let's say we just have a point charge at the end. What is our electric field going to look like due to that point charge at the end? What's the electric field due to a point charge?
AQ over R squared.
Exactly, KQ over R squared. So, what is R in this case? What is R squared?
Normally it's the distance from the charge.
And so, how do we find that in terms of things we know? How do we get this distance squared?
You know how far away it is in X and Y direction, so you can just use like Pythagorean theorem. to find
Exactly.
it.
Exactly, Pythagorean theorem. So, for our individual point charge, it's going to be KQ over, we'll call this X naught to Y naught up here, and then we'll integrate over X. So we have R squared is going to be X naught, because this distance along here is X naught. And so we have X naught plus 2, because we have the extra 2 here. X naught plus 2 squared plus Y naught squared. Right? That's our electric field. E is equal to KQ, X naught plus 2 squared plus Y naught squared. And in what direction? Well, it's going to be in the R hat direction, right? In this direction. Let's break that down into X and Y components. How would we break it into X and Y components?
So, would it be the sum of all the X components?
Let's not worry about the sum of all the stuff. Let's worry about just this individual point charge at the end here. How do we get the X component of the electric field from our point charge at the far end?
The cosine.
Cosine. How do we get the cosine?
To take the angle.
So this angle.
Yeah, right there.
So we want the cosine of that angle. How do we get that in terms of things we know?
The adjacent over hypotenuse.
Exactly. Adjacent over hypotenuse. So it's going to be X naught plus 2. That's adjacent over the hypotenuse, which is the square root of this, right? So I'm just going to do this. I'm going to throw the X naught plus 2 up here and just go ahead and raise this to the 3/2. Boom. That's our X component. And now, what about our Y component? what's our y component going to look like?
You would take the sine of the same.
Sine of the same thing. And so what's sine?
It's opposite over hypotenuse.
Exactly. So we would have y naught up top, and we raise this to the 3/2. Now we have the y hat direction. Boom. There's our x component and our y component for the point charge. So now, how would we actually go ahead and set this up to integrate over the whole line of charge? Well, we're integrating the charge, right? We're integrating Q. So let's go ahead and replace Q with dq. How do we actually get dq in terms of something we can actually integrate? Well, remember our total charge of our line, Q is going to be lambda L, right? If we take the derivative of Q with respect to something we can integrate, what's it going to be? Well, lambda is a constant, right? And I'm thinking, let's go ahead and integrate with respect to the length. dq is going to equal lambda dl. And in that case, that dl is actually, we'll call it a dx, because we're integrating along the x-axis. So now we just throw it into an integral, right? And we integrate from -2 to +2 on the x-axis. So ex is going to be the integral of k lambda x naught plus x, because our 2 here, it's actually going to be x naught minus x, k lambda x naught minus x dx over x naught minus x squared plus y naught squared to the 3/2 from -2 to +2. And then EY is going to be the same thing, except we throw in y naught instead of x naught minus x. Does that make sense? Does anyone have any questions? Now this might seem a little,
Got it.
it's a little unintuitive. It takes a bit of practice, but it's just getting comfortable with understanding that first of all you need to you need to set up an integral, and then how you actually set up the integral in order to integrate, and that's how you would get the actual electric field everywhere. And then when we're very close, then we know that y naught is effectively going to be y naught would effectively be 0, and then when we're very far away, then our y naught and x naught are basically going to be negligible, and it's going to end up canceling out into what we found in A and B. Does anyone have any questions about that? All right. So let's go ahead and hop into one more example. We're going to have a Gauss's law problem. Now this is going to be a little more comfortable for you guys, since this is what you guys were doing a lot when you guys were doing electric fields. So we're going to have a cross section of a very long straight conducting line of charge. Hint word there, conducting line of charge. And we have a linear charge density, -2 lambda naught. It's going to be surrounded by a hollow conducting cylinder, inner radius B, outer radius C, and a linear charge density +3 lambda naught. So first thing I want to know is, how is our charge on the inner line of charge going to be distributed? Anyone want to shout it out? What is our charge going to look like on our inner line of charge? You actually go ahead and... Oh, that didn't work. Go ahead and yoink this image. Toss it into paint.
I think the keyword there is the conducting line of charge.
Mm-hmm, exactly.
So it's going to be on the outer.
Exactly.
Right rule.
So it's going to be all on the outer edges. So it's going to look something like this. So we're going to have a bunch of little negative charges all along the outer edge. And so now, what is our charge going to look like on the outer line of charge? What is it going to look like?
They're both going to be. I can't really read the numbers that well, but I think that it's a larger magnitude. It's positives, so that means that there's going to be a positive inside the radius, and then also positive on the outer radius as well.
Yep, exactly. And so, what's special about this? About the magnitude of the positive charge on the inner radius?
It is less than magnitude of the outer one.
Not necessarily. I'm talking more related to...
It's for the charges? Oh, yeah, you would have to look at area, right?
Not quite what I'm looking for. I'm talking related to the charge that's on the inner wire, the inner line of charge. How is this charge on the inner surface of the outer wire going to be related to the charge on the inner wire?
They're the same. Like,
And why is that?
nature.
Nature. Excellent answer. You might get a point for sarcasm on the test. What about
I just said
nature?
that they're attracted to each other. That's
And why would they have to be equal? Why would they have to be equal in magnitude? If it's all about attraction, why isn't all the positive charge on the inside and nothing on the outside?
a balance.
Similar keyword from before.
Well, those positive charges are also repelling against each other as well, right? So, there's going to be a buildup of positive charge on the inner radius, but it repels the inner radius repels the outer radius. I don't know.
You're overthinking it a little bit. What sort of material is our hollow cylinder made of?
It's a conducting shell as well.
It's a conducting shell. What's special about conducting shells?
They're not uniformly dispersed with their charges.
More specifically, what's the electric field inside a conductor look like?
Inside, in the middle, 0.
0, exactly. So why is this magnitude on the inner part equal to the magnitude on the inner wire?
That's all I know. I mean, like, I understand. I've always understood that it's 0 in the middle, but
Mhm.
like, why wouldn't it be all of it?
Like, I'd say the charge that would be, distributed throughout the model 2 is just on the edge. At least that's how I think about it conceptually as a Y. Well,
You guys are missing an obvious one here. Gauss's law. Q enclosed has to be 0. Right? If we have a Gaussian surface through the middle inside our conductor, we know the total enclosed charge has to be 0. So
All right, I see.
So so we have -2 lambda naught here. We're going to have +2 lambda naught here, and then our remaining +1 lambda naught on the outside. So now, how do we actually get the surface charge density on the inner line of charge? We're given the linear charge density -2 lambda naught. How do we go from that to a surface charge density? Sigma.
Times L. Oh, sorry.
Well, go ahead.
Lambda times L should give you your charge, right?
Yep, so our total charge is equal to lambda, so it's -2 lambda naught times L. What is L?
Length of the wire.
It's an infinite wire, right?
Yes.
So you're saying L is just an arbitrary length of it? Because wouldn't L be infinite? I'll admit, I'm being a little malicious here. I'm trying to bait you into overthinking the problem. Let's just call it L. It's just an arbitrary length of it. And let's not worry about it, because it's actually going to end up canceling out. So we have our total charge. We have our charge density times our length. Now how do we go from this to a surface charge density?
Surface charge density is equal to charge over the area. So you could also set charge equal to surface charge density times the area. And that's how your L's would probably cancel out.
So we have the area. What is the area along our cylinder? So you cut out for a second there. Did you repeat? What's the area of a cylinder? What's the surface area of a cylinder?
It would just be 2 pi RL.
Exactly.
Yes.
So it's going to be, we have our negative, our 2 is going to end up canceling out. So we have negative lambda naught. L also cancels out over pi r. Our radius is r is just a. So negative lambda naught over pi a. That's how we go from a linear charge density to a surface charge density. We get our charge, and then we go from charge, we divide it by the area to get our surface charge density. And we could do the same process for the inner surface and outer surface of our outer shell, but it's going to be very similar, and it's just going to be using different numbers. So now, how would we actually go ahead and find the potential difference from the surface of the inner line here out to point P? how would we go ahead and find that potential difference? What would we need to do? Could you repeat that?
Voltage, off the top of my head, voltage equals electric field times the distance. So
Well, not quite the electric field times the distance. It's going to be an integral of the electric field over the distance. Or delta V is going to be
yeah, that is from the voltage from A to B is the integral from, or the negative of the integral from A to B of the electric field times.
Yep. So we have going from A to point P of E dot dl. How do we get the electric field?
You can do like a point charge.
Point charge.
Like if you want to find the electric field at that location,
How do we find the electric field? So the electric field isn't completely uniform throughout this whole path from A to P, right?
right?
So first of all, let's find it. Well, we already know it in here, right? 0.
Find what Q would be, right?
Hmm? Yeah, you keep on like cutting in and out. I think your mic has some issues picking you up.
Sorry.
It's like each time you start talking, it's like I hear you for a split second and then it cuts out and it comes back in about a second later.
I'll stop talking.
So, what law do we use to find the electric field? It starts with the G.
Just Gauss's law?
Just Gauss's law.
Right. So, you wouldn't need like a complicated example, would you? Because like,
No. And honestly, I'll give you a hint. By virtue of Gauss's law, you could just say, oh, Gauss's law, it's symmetrical. It looks like a line of charge to the center.
right, so it's just the charge contained.
Mm-hmm. So what is our electric field going to be between A and B? Call it E1.
That would be oh shoot.
What's the electric field do to an infinite line of charge?
I'm like here.
Well, you can get it from your formula sheet, Unit 6. It's going to be 2k lambda over r.
Lambda.
So then our electric field, lambda in this case is negative 2 lambda naught. So we have negative 4k lambda naught over r. And so now what's our electric field between B and C? Inside our conductor?
Um,
0.
0. It's a conductor. And so what's our electric field outside between C and D? We'll call that E2. What's our total enclosed charge?
one lambda naught.
It's positive 1 lambda naught. So then our electric field is going to be plus 2k 1 lambda naught over R. So then our potential difference, our total potential difference, go ahead and expand this downward. Our total potential difference is going to be, we're going to add up our two integrals for E1 and E2. It could be negative integral from A to B of negative 4k lambda naught over R dr, because dl is just dr in this example, minus the integral from b to c of 0 dl, so it just goes away, and then from c to d of 2k lambda naught over R dr. Boom. If we go ahead and actually solve these integrals, what do we get? What's the integral of 1 over R dr? We can go ahead and take these. Oh, go ahead.
You said E1. That would be, you take out the 4K and the naught, and then
Mm-hmm. And then we have a
1 over R dr
Mhm.
would be, it would turn into ln
Yep. Exactly. Natural log.
R.
Yep, natural log of R, which if we evaluate from A to B, that's just going to give us the natural log of B over A. And we have minus 2k lambda naught natural log of D over C. Because it's the same process. 1 over R dr becomes natural log. Does that make sense?
If I could cycle back, so I think where I got lost a little bit,
Mhm.
it'd be finding Q for like E1 or E2. I guess finding, looking at the picture, I just lost it myself. 'Cause,
Yeah. So here, let me redraw it. But sort of essentially what we have here is we have a cylinder along the center. This is radius A. And along the length of the cylinder this way, we have a charge density of minus 2 lambda naught. And then surrounding that cylinder is another larger cylinder. I'm sort of drawing it obnoxiously large just so we can actually visualize things a bit better. And along this outer cylinder, it has a total charge of plus 3 lambda naught. Does that sort of help out?
Right. So when we're returning from like our first electric field, it was like from A to B.
Yep, so we're in this space.
Something like that.
We're in this space between the two cylinders.
So that would account for the 2 lambda naught on the negative 2 lambda naught from the cylinder,
Exactly.
and the positive lambda naught on the inside of the cylinder.
Would we have to worry about that?
Oh well, they're both like enclosed, right? So
What's Gauss's law say? E dot dA is equal to
that would be 0.
So wait, are you talking about between the two cylinders, or are you talking about inside the outer cylinder?
Between the the two cylinders.
Yep.
I'd say.
E dot dA is equal to Q enclosed over epsilon naught. Right? If we draw our Gaussian surface in between the two of them, what charge is enclosed?
It would be two lambda naught, negative 2 lambda naught.
Yep, literally just the negative 2 lambda naught. Everything else is outside of it. Doesn't matter. We ignore it.
Oh, and then you would take the same thing for the inside
Mhm.
the cylinder.
Yep. We do the same thing inside the cylinder. Another Gaussian surface. The total enclosed charge is 0. So the electric field is 0.
Right.
And then we take a third one outside the whole thing. The total enclosed charge is what?
Be 1 lambda naught.
Exactly. Did that help out? Is that where you got lost?
Yeah, I'd say finding out that Q for like E1 was 4, negative 4. That's where I like saw the disconnect. But
Oh, that's just because the formula itself, E is equal to 2 K lambda over R, and we plugged in negative 2 lambda naught for lambda.
okay,
So the 2's, we multiplied the 2's together.
okay, I think that's where I lost it. All right.
Perfect. Anyone else have any other questions? All right. Well, if that's the case, I'm going to go ahead and wrap up the session. I'm going to host one more exam review session tomorrow. Going to be focused a bit more on circuits and magnetism, but we'll still have one little electric field, probably Gauss's law example, tomorrow. Earlier in the day, because Dr. G is hosting some office hours, so it's going to be at 10 tomorrow morning instead of the usual 1 o'clock. Spread the word. See if we can beat my attendance record from last spring. Probably not. I had 97 people to show up to one session. But yeah, 97 people. It was absurd.
The whole class.
It was literally like it was right when things first went online, and I think people were still in that phase of like sort of being excited about the sudden change. And let's put it this way. It was live lectures. It wasn't Dr. G. He was on paternity leave. It was Dr. Warcheski teaching the class live on Blackboard Collab, and it was literally just Twitch chat spam the whole time. It was wonderful. It was beautiful. And then, oh my God, there's an SIPass Discord. Everyone join. Oh, there's a memes chat. Holy shit. Oh, there's an exam review session. Let's all show up. All right. Well, I got to go. I got a class in half an hour. I need to actually run to campus real quick and drop something off. So, thanks, guys, for coming. 10 o'clock tomorrow. Exam review session focused on circuits, magnetism, all that jazz. Have a good day, guys.